Hello, my name is Stanford Gibson. I am the sediment transport specialist at HEC and in charge of the sediment transport capabilities in HEC-RAS. And this is the second video in a multi-part series on reservoir sedimentation modeling in HEC-RAS. In the first video, we talked about two different ways to model a long-term sediment deposition analysis in RAS using the quasi-unsteady approach. The next video will move to unsteady, but the two ways to use the quasi-unsteady approach are first to end the model just upstream of the dam and use the cross-section just upstream of the dam as the downstream boundary condition by defining the reservoir stage as the downstream boundary. And the second is to go ahead and build your model, including reaches upstream and downstream of the dam, but to actually go ahead and put in an inline structure, but then the quasi-unsteady approach won't be able to route flow through the reservoir. And so in order to have a structure in your dam, in order to say model the downstream reach at the same time or multiple dams in series, you'll want to go in and define an internal stage series to simulate the reservoir stages. And the kind of the moral of the story for using quasi-unsteady to simulate reservoirs is there's a couple of different ways to do it, but you're going to have to know the stage time series of the reservoir, either because it's been measured historically or because you ran a hydrologic model outside of RAS, but that's data that you will have to bring to the table. If you want RAS to kind of route both water and sediment through the reservoir, then you'll have to move to the unsteady flow model for reasons that we'll describe in the next video. The last video went into much more detail about these different approaches. This video will actually just step through the practical steps of setting up both of these types of models. You'll find a link to the files you'll need to follow along in the description of this video, and there's really not a lot of them. We've given you a project file and a geometry file, and then some data you'll need for building the reservoir, mainly the hydrologic time series. We're going to move kind of quickly through the steps of setting up a quasi-unsteady sediment transport model. We have a 3-part video series that steps more carefully through those steps if that's your interest. But here we're going to really focus on the process of setting up a reservoir model. And so if you open up the project, it'll open up a geometry file that looks like this. This geometry file is completely fabricated. It is not based on any system anywhere on Earth. Please do not use it for project or scientific analysis. It's entirely fictional and was developed entirely for this educational process. The dam is going to be at station 1000. So the first approach to modeling a reservoir and quasi-unsteady flow is to make the cross-section upstream of the dam the downstream boundary condition. So let's do that first. We'll go and we'll save this geometry data as, and we'll call it something like downstream boundary at the dam. And so then what I'll do is I'll go in and delete all of the cross sections downstream of the dam. I push this arrow button to say, yeah, those are the locations I want to delete. Press OK. It'll ask me, do you really want to do this? Because it is rather dramatic. And I'll say yes. And so now I'm left with a downstream boundary condition that is close to the upstream face of the dam. So I will save that. And then I will go and define my quasi-unsteady flow data. I'll press the quasi-unsteady flow data button, and I will get the quasi-unsteady flow data editor, and the upstream boundary is going to be a flow series. I've given you a data file with some flows, and you can see that the flow data starts on January 29th, 1968. So we'll select flow series. We will switch to fixed start time because we do know the start time, and that is going to be 29 July 1968. And it has to be in that exact format, and your computer actually has to be set to read US customary dates and then time 000. And then if we look at what our time series is, we actually have over 18,000 dates. And so we're going to set the number of ordinance to 18577 to make sure we have enough flows. These are daily flows, and right now we're going to run at a daily computation increment. If I was doing this as a project, I probably wouldn't use a daily computation increment, but I wanted to have a decent runtime, and it actually works out pretty well for this analysis. And so I'll hit interpolate values in order to get 24 hours throughout there. And then I'll just come here and press Control Shift down to select them all, and Control C to copy. And then here I'll click on the heading to select the column, Control V, and press OK. Now I have a flow series. If I reopen it and press plot, you can see the flows, and this looks like a standard unsteady flow series until you really zero in. But if you zero in, you can see that this is actually not a hydrograph, it's a histograph. It's a series of steady flows. Okay, so then we're going to enter our downstream boundary condition. And remember, our downstream boundary condition for this approach is just going to be this stage of the reservoir. This is where if you have a time series of your reservoir stage, you would just go and put it in just like you put in the flow series. Just to simplify this problem, I'm going to specify a constant reservoir stage, just so that we can kind of get an intuitive sense of what this reservoir does. And so I'm going to give it the same fixed start time, 29 January 1968 at 0000. You could just go in and do 19,000 daily stages, but the way I like to do it is I just give it a pretty large duration of say 24,000 hours and give it a stage of 555. Then if you hover over this, you can drag it down. And then if you open it up, you can see that you have coverage well into the 21st century. And so this gives you a constant downstream stage boundary condition that should easily cover a 50-year simulation. The other thing you need is temperature. And like stage, you can put in a temperature time series. A lot of times you define an annual curve, but we're going to put in a constant temperature just like we did with the stage. And all that 24,000 does is it creates the input duration, and we're done. And so now we have a quasi-unsteady flow file, and I'm going to call this downstream boundary at dam. All right, and then we need a sediment file. So I'll open the sediment file. So this is a reservoir model, so it should mostly deposit. So the max scour depth doesn't matter much, except it will matter a little in the upstream end to make sure that the reservoir isn't unduly scouring at the upstream end. So I'm going to just put an arbitrary max scour depth of 10 meters in there. I'm going to set the movable bed limits to the bank extents. We can interrogate that assumption later, but it turns out in a depositional model, as long as you allow deposition outside of the movable bed limits, it doesn't really matter that much. And then finally, we need a bed gradation. Now, because we're starting from the very beginning of the dam, we need a gradation of the river before the dam was in place. This can sometimes be hard to get. You could get a gradation upstream of the dam. In this case, this is a very steep system and a very coarse system, and so we're going to go with a very coarse armor coverlet. So if I open the define edit bed gradation, and I'm going to call this coarse cover, and then I gave you a gradation in the data file provided. And so I'll come here and get these percent finers starting with the first field, and then if I come over here and paste those in, we get a gradation. I say okay. I'm going to click on the gradation field and select it, and then drag it down. And we've defined our initial conditions. I'll give it a name. So there are two options that are very important to select correctly in a reservoir model. The first, if I come in here and say options, bed change options, we set the movable bed limits to the bank extents, which means that as a default, it will only deposit in the channel, which is not the case with the reservoir. The reservoir is going to inundate the entire floodplain. And so we want to make sure that we allow deposition outside of the movable bed limits. And then this update between mixing time steps is just a numerical improvement we made to improve performance of this particular feature. And so we'll say okay. And then the other thing we want to do is go to select routing method. Quasi-Unsteady solves the Exner equation, which means that we just move sediment by continuity, which means we don't really keep track of where the sediment is. We just kind of pass it from control volume to control volume. But what that does in a reservoir model is a lot of times it underpredicts deposition because the model doesn't actually keep track of residence time in each control volume, and so it passes it downstream too quickly and doesn't give the sediment enough time to settle. And so we have another option. It's kind of a quasi-advection option where you can select limit to water velocity. What that does is it limits the sediment velocity to the water velocity. It keeps track of how much sediment actually can move through the control volume in a time step and accounts more carefully for the amount of sediment that can deposit in a time step. So we'll say OK. Then the last thing we have to do is choose the algorithms. The fall velocity method is fine. The sorting method, the Thomas method, was actually developed for computing armoring downstream of a dam in a coarse high gradient system, so that's perfect. And for the transport function, we're going to switch to Larson-Copeland because it's better over the gravel and cobble range. And then the last thing we need to do is define the boundary condition. This is the upstream sediment boundary condition, and we're going to define a rating curve. And I've created a flow load rating curve here with gradational breakdowns. You might ask, how did I come up with this? The answer is because this is a synthetic data set, trial and error. I developed a flow load gradation rating curve that seemed appropriate for this data set that I'd concocted on a steep slope with coarse material, but then adjusted it until the upstream boundary condition was in equilibrium. And so I will paste that here. And we're done. So we'll save. Open the Quasi-Unsteady analysis window now, and I'll say this as, to give it a name, short ID, and then I'll give it the dates of the simulation. And so I want to run a 50-year period of record simulation. So I'm going to run from 29 July 1968 to 29 July 2018. And then I'm ready to compute. So this took about 3 minutes to run on my machine. And let's look at the results. If you go to View and Sediment Results on the bottom, there's actually two ways to view sediment results. There's kind of the newer way and then the old way. These output viewers have different strengths and weaknesses. We actually have a new output viewer that combines the strengths of both of these in 5.1. But for now, the way that we want to view results, it's best to go to the old sediment spatial plot. So let's open that. The sediment spatial plot comes up with the channel invert as the default at time 0. I like to also go in and add the water surface elevation. Incidentally, this is why I'm using the old viewer here, is because in the old viewer you can view multiple variables at once. And you'll notice that, in fact, we are using the downstream boundary condition as the reservoir stage, and then it transitions to run-of-river flow upstream of that. And then we're also going to turn on the final profile. Now, I don't love the default colors here in RAS, so I'm going to go in and change the lines and symbols. And I'm going to change my bed material so it's a brown line, and let's make it a little thicker. And then I'll change my second water surface elevation so that it's a different shade of blue. And so now we can see here's the initial bed elevation and the final bed elevation, as well as the initial water surface and the final water surface. Now there are a couple of things to notice here. One is that we have in fact formed a pretty nice delta that has prograded into the reservoir. You know, if we go in and turn on an intermediate time series, we can see that it is in fact making its way somewhat gradually down the channel, but also that it's fine enough at this slope to be more of a tapered delta. The second thing that's worth pointing out, I'll phrase as a question. How far upstream do the effects of the dam go? It's actually a really important question because you can see that the sediment impacts of this dam actually go quite a bit farther upstream than if you were to just draw the high water profile to its intersection point of the original thalweg. And the hydraulic impacts of the dam go farther upstream still. And so this is actually one of the important principles for building a reservoir sedimentation model, is that even though we're going to set the downstream boundary condition right at the beginning of the reservoir, the upstream boundary condition should not be right at the beginning of the reservoir. The upstream boundary condition should be substantially upstream so that we can actually capture the upstream impacts of this reservoir. A lot of people will actually just draw this reservoir pool until it intersects with the thalweg and make that the upstream boundary of their cross-section, but that actually underestimates the impact of the reservoir sedimentation. So that's the first method I'll demonstrate on how to model a reservoir in quasi-unsteady sediment. The second method is similar, but it extends downstream of the structure. This is when you want to model a longer reach and you just really don't want the downstream boundary condition to be at the dam. But since quasi-unsteady flow, you also can't let the reservoir just kind of route the water. And so what we're going to do is we're going to set up an inline structure inside of the dam and then define an internal reservoir stage. So to do that, we're going to want to go back to our original geometry, select geometry without dam, and we're going to use the entire reach, but what we're going to do is we're going to add an inline structure. And we'll add an inline structure by going to Options, Add Inline Structure, and we'll give it a station of 10,000. And then we'll give it a very simple embankment. We'll go from 0 to 1,000. We'll give it an elevation of 560. So that'll drop an inline structure right there where the dam goes in the geometry. Now, one of the things you might run into in RAS is that when geometries are different, when you have a different number of cross-sections, different upstream and downstream boundary conditions, it's often helpful to start from scratch with the boundary condition data and the sediment data so that RAS doesn't get confused about mapping. Instead of starting with the sediment data that you have in your other file and saving as. And so we're going to come in here and we're going to create a new quasi-unsteady data. We'll call this internal dam. And you'll see that this will populate only with the data that we need. And so we'll go and do exactly the same boundary conditions. And I'll try to do this a little bit faster just because so much of it is very similar to what we just did. Okay, but then the one thing that is different is you're going to have to go in and add an additional boundary condition. And you're going to add it at this upstream cross-section, which is essentially exactly where you had the downstream boundary condition in your last model. And so now we have a blank boundary condition, and there's only a few things that are available for this boundary condition, but we're going to use the internal stage boundary condition. And so basically we're going to treat this the same way we treated the downstream boundary condition in the last model. We are going to set the reservoir stage, and again, if you have a detailed reservoir stage time series, you can use it. We're just going to go with a constant just for demonstration. Okay, and then of course we're still going to set the temperature in the same way too. Okay, so we have our Quasi-Unsteady data. Now before we continue, there's one important note about inline structures in RAS sediment simulations. That's that inline structures, dams, whether or not they have gates, are pass-through nodes. A pass-through node in sediment transport just means that all the sediment that comes to the node leaves the node. They're not control volumes, but more importantly, we don't decide how much sediment can pass through them based on the geometry of the structure or the location of the gates. You could imagine these three dams that I'm showing right now would have pretty different sediment behavior as far as what kind of sediment would pass through them, and we ignore that in RAS right now. We're working on features, but the reason is that in general, this doesn't turn out to be as egregious an assumption as it seems like it would be. Except for really small reservoirs or reservoirs where the delta has approached the dam. By the time water reaches the structure, often the sediment that remains in the water is wash load, is the kind of material that could go through or over most gate configurations. But that's still an assumption that you want to assess and make sure that you're not over predicting flux through the dam. The second thing you want to consider with respect to these structures and the modeling strategy we're talking about is that if the dam doesn't have any gates, then you can simply define an internal flow boundary condition and RAS will compute a backwater through the gate in a quasi-unsteady form. But if your dam has gates, then even though we're not using the gates, even though we're not routing flow through the reservoir, gates are a mandatory boundary condition. So here you see a quasi-unsteady flow series on the left that has no gates and a quasi-unsteady flow series on the right that has gates. In both cases, we're defining an internal stage boundary condition just upstream of the dam, but for the one that has gates, we have to define a gate opening time series, and this can just be a dummy time series because we're not going to use it. We're going to use the internal stage boundary condition to determine what's happening through the dam. But because it's a mandatory boundary condition, you have to go in and give it data. Let's open our sediment data. And in the same way, you can see that this is going to get confused about the boundary conditions. So let's just go in and create a new sediment data. And we'll select our transport function. We'll set our max depth. You can see that there's a gray field for the structure. RAS will allow you to specify data in there, but then we'll blank it out. And then we want to go make sure we go get those two options. Our bed change option, we'll make sure that we've got the overbank deposition on, and the routing option, we want to make sure that we've got our simplified advection model working. And then we're ready to go. We're going to create a plan, and we'll call this internal dam. And all the plan data will stay the same. So we can press compute. And it takes a few minutes to run. And now if we go to the sediment output, you can see that we have a kink in our geometry here where the dam is. And if we turn on our results the way that we looked at the previous results, see the results are very similar. I'll compare them in a little bit, but you can see that one of the major differences is that while we get a very similar depositional pattern through the dam, downstream of the dam, we're actually getting scour, which is what we would expect from a reservoir like this, that if you intercept a substantial coarse load, that there would be scour downstream of the dam and then eventual armoring. And so you can see that by introducing the dam in the middle of the domain, we're able to model both the upstream and the downstream effects. But of course, the downside of both approaches is really that you need to know, either a priori or from an outside analysis, what the stage of the reservoir is going to be. And that can be easy enough for a historic simulation if you, say, have some sort of measurement of the reservoir stage, but it can be particularly difficult if you're going to predict and try to simulate your reservoir into the future with no real knowledge of what that reservoir stage would be outside of some sort of hydrologic modeling. And so the next step would be to actually simulate the water and the sediment together, routing both of them through the reservoir. And to do that, you're going to need to use unsteady flow, which is what we'll talk about next. And just to wrap things up with a comparison, this is the initial and final bed profiles for the two simulations. You can see that the two simulations basically plot on top of each other after a 50-year simulation. The difference is that the simulation that includes the dam as an internal boundary condition also computes the downstream scour. And so we'll wrap up this two-part quasi-unsteady demo here and transition to the next series of videos, which will focus on unsteady flow. And then eventually we'll get to drawdown flushing and reservoir sediment management. This work has been funded by the U.S. Army Corps of Engineers, both the development and the videos, by the Flood Risk Management Research and Development Program, and also in part by the Regional Sediment Management R&D Program of the Corps of Engineers. And we'll see you in the next video.